too low, then you couldn't drive. There isn't enough potential difference to drive the motor. Then how else can we lower the speed of that motor? So there's a technique that's called house speed modulation, or you often get here TWM, house speed modulation. So there's one technique that you could use to control the speed of the motor. Because you no longer vary the voltage directly, but you sort of vary the power that's going into the motor. So later on, you get to see that. There are also some other ways to control brush DC motors using EWM. H-bridge, which we will be seeing, we use that to rotate the motor clockwise or anti-clockwise. You can see the control block diagrams, transfer function of the motors, particularly looking at two cases. One is that the motor is driving a load directly without a gear, and then we look at what is the output load position to the rotation. The other transfer function that you get to see will be motor system with a gear, reduction gear. So you have seen before, I think about 2 lectures ago, and we were trying to establish that. So today you get to see the entire block diagram. That one is to allow us to know what is that load position to the armature voltage. And we also talk a little bit about the torque requirement of the motor before we end up with an example. So the microprocessor is something that we use a lot to control the motor. Particularly, you heard so much about this signal, digital signal, 1 and 0. I wonder, have you ever wondered what is those 1s and 0? I know it's a digital signal, but there's a certain voltage behind it. And recently, these 1s and 0s came down to be at a lower value because there are some efficient microcontrollers these days that runs on 3.3 volts. Last time, during my time, it was all 5 volts to run a processor. Nowadays, Texas is one of the leaders in having this low energy microprocessor that runs on 3.3 volts. So that's very low voltage. So your microprocessor will send the signal 1, 0 to the motor. That has to be converted. Later on, you get to see other techniques as well. So these 1s and 0s, that 0 over there doesn't mean that this is 0 volt. It's anything that's less than 0.8 volts will be recognized as 0, right? The peak 0. For the peak 1, is anything that's above 2.4 volts. Here, 2.4 volts and above will be recognized as 1 peak. So you have your transistors inside the microcontroller. Just putting this on off switch. How do you know what is on? Just applying that voltage. If you want off, then you apply less than 0.8 volts. If you want to turn it on, then you supply more than 4 volts. So that's just about it. All your electronics, all those things that are using our digitized signal. So in order for the microprocessor to be useful, there must be input and output of the microprocessor. Normally, because your microprocessor is a digital equipment or a digital device, So you couldn't read analog signal basically. Discovery with analog. 8 and 8 which is scale, so you can see that one. So if you have an analog signal that's coming in, this. Now the analog signal cannot be read by the processor directly. So you gotta have an analog to digital converter. That's where it is sensed. So this will be your senses. And after you have sensed that information, you will want to do something about that information. For example, do a calculation, and you put out a signal to drive, for example, a motor, right, to some actuation. So that part here, this part here is digital signal, and it's always a digital signal coming in out of your microcontroller. So you need a digital to analog converter, and that will go into your actuator. So sometimes, depending on the actuator and the sensors, some sensors actually exist as a it gives off a digital signal. An excellent example would be your encoder. The encoder would provide that digital signal that can be read by your microcontroller directly. There are also actuators that reads digital signal directly. So is that different combinations? So if you have that as your analog actuator and analog sensors, then you need to have AD converter or DA converter. So then how do we make use of this DAC converter? DAC converter. When we want to have that digital signal to be a converter into an analog signal. Say for example, if you are using a brushed DC motor, your brushed DC motor will not be very your digital signal. Actually, what happens if you put a digital signal into your DC motor? Have you ever tried that? What will happen? Actually, nothing would happen because your analog motor cannot read a digital signal, cannot receive that digital signal. Actually, that's why there's not going to be anything. So you need a DAC or digital to analog converter coming in. And this is the part that I included myself because if you're wondering how does it work, how does the DAC converter, how does it work? Say for example, if you have an 8-bit DAC converter, 8-bit DAC. It's not very high, it's about 8 bits. So 8 bits will be giving you 2 to the power 8 or 256 digital input values. So you have 256 digital input values. And in order for us to calculate the analog output voltage, say for example, if we are interested to have out of a 5-volt system, we are interested to have 2.5 volts, then what sort of digital input will be necessary? So you take 128 divided by 256 multiplied by 5, and you find that you get 2.5 volts. So that number 128 is something that your microprocessor will be generating. This one generated by your micro. So your microcontroller can keep whatever number of bits over here. So depending on that number of bits over there, if the total output of your microcontroller is 5 volts, maximum 5 volts, then you can use that controller voltage. Now, why is this voltage control important? That's because this voltage over here will determine how fast you want to run, for example, your motor without using a potential meter. So this is something that you can do using a DC converter. So you can see that depending on the number of bits, if it's n-bit DSC, then you get respectively a higher resolution for the kind of voltage adjustments that you can have. So this on and off bit is actually done by your transistor. So when it's fully on or off, then power loss is 0. It's fully on, that is at the state of 1 or the state of 0. So at any of these states, 1 or 0, your transistor does not consume any power. Power loss. The power loss is almost 0. It's only in the process of switching from 0 to 1, or from 1 to 0, that process of switching over, and actually a lot of heat is generated. So if you're using a transistor to do rapid switching, right, you want on-off rapid switching. Why this rapid switching is desirable is because you're after that PWM signal, the on and off PWM signal. So if you're after that, a lot of switching, you get to see that your transistor will heat up tremendously under higher switching frequencies. Because higher switching frequencies means that it spends more time in the process of switching. If you switch to 0 or switch to 1, then you actually don't have much power loss. That's the nature of your transistor. So So there's some definitions behind PWM. I think the easiest way for me to do a demonstration of PWM is to control this light. So what I could do is to control the light. It's off. It is on. I have a 50% duty cycle. Right, 50% duty cycle. I can do this faster than that. That means at 50% duty cycle, what I'll do is increase that frequency. So you can see that it's not like trying to turn on, trying to turn off. It has a certain latency, or we say that it's this inductance effect. What I was trying to demonstrate is that you can see that if I were to switch the light at 50% duty cycle at a fast enough speed or higher frequency, you find that the light is kind of not fully on. You get partial lighting. That partial lighting is actually what we want. The amount of power that's driving the light now has been reduced. And if it has been reduced, what that means is that we don't need a voltage divider. We can just use this sequence of turning it on and off in order to control the amount of power that's going into our device so that we don't drive it at its maximum capacity. Why is driving at its maximum capacity not desirable? Well, that's because we want to have a sense of controlling energy or the power that's going to our device. Right? We don't really turn on a motor just on or off. We want to control the speed. So this controlling of the speed can be achieved by controlling the amount of power that's going to be. So that's what we're trying to do.
could see that what I was doing is varying the length of time when it's on or off, such that I'll achieve an average effect or average effective voltage. So if I were to do a sketch of that PWM, this is how it's going to look like. So we have some definitions over here. From this point here to this point, this one over here, T1. T1 is called your power duration. And T, from this point to that point over there, T will be called your power separation. So you can see that the output voltage, right? This one is your maximum VCC voltage. The output voltage will be taking that T1, which is a power separation, divided by T, that's a power separation. Taking that ratio, multiplied by your VCC, that is your effective average voltage, which is represented by this dotted line. So if I were to do a few more sketches to give you an idea of the effective V out. Let's say I have a case of a 50% duty cycle. So I have mine, this is voltage and this is time. So this is VCC. So at 50%, what that means is that over here, that will be your T, and this will be your T1. So if I look at, say, 10%, at 10%, again, your VCC, you supply a pulse that's just 10% of your entire T. So this one will be your T1. So T1 divided by T, that will give you 10%. Okay. So the average voltage will be over here. If I have 90%, again, your VCC is going to be here. So 90% of that over here. That will be your T. This is your T1. So you get an average voltage that is here. So you can see that what I'm trying to do is to play with the duration of my powers. The longer that duration, the closer it is to the 100%. So if I have 100% VCC that's applied, that means I just turn on my motor continuously at that highest voltage. So I'm not controlling the speed at all. Now, normally this house rate, although it's 50% over here, but I could have a 50% at a lower frequency or a higher frequency. So, for example, at a lower frequency, this at a higher frequency. This is 50% as well. There's also 50% as well. So you can see that this is at a lower frequency, and that is at a higher frequency. Both are 50% duty cycle. So essentially, this part over here will be your duty cycle. then how high a pulse rate we can go? How high a frequency? Usually is about 2 to 20 kilohertz. That's sort of PWM signal. And you will want to have this pulsing of PWM, avoiding the natural frequency of your motor. Now your motor, as you operate it, you will actually resonate at certain frequency. And this frequency normally is in the lower frequency. It's in the lower frequency. So when you have PWM, you just need to make sure that your PWM is not pulsing at a low frequency. Right? You can have the same duty cycle at 50% at lower frequency, or same duty cycle at a higher frequency. You can choose the one that's in a higher frequency that will avoid the natural frequency of the motor. If you have PWM frequency that lies in the range of your natural frequency of your motor, is going to affect its performance. So please try to avoid that. Your motor, just like the lights that you saw just now, is essentially just like a low-pass filter. So it behaves just like a low-pass filter. So it doesn't respond to the trigger of on and off immediately. Right? It responds after a while. So the disadvantage of using the PWM is that you get to hear some audible noise. In fact, I think last week when I was trying to show you a video with the whining sound of a PMAC motor, your AC motor that's used in a SMRT, you get to hear this whining sound that is picking up the velocity or the rotational velocity. That whining sound is a sound that's audible if you use PWM. So if you switch it at a very high frequency, it gets into your audible range. So you got to kind of like play with that frequency. Make sure that it avoids the natural frequency of the motor, and yet it wouldn't irritate us because we can start hearing those audible noise. So I think I talked about this before. The heat generation is doing this switching. So at very high switching, you can actually use two types of transistor. One will be a MOSFET. The MOSFET will be used for low power application, and if you have high power switching application, then you use IGBT. I'll define both of them. The MOSFET would be metal oxide semiconductor. Effect transistor. So it's a kind of transistor that's for low power. So some of you may be already using MOSFET in your FYP. That's tend to be because you're using that for a low power application. If you have high power needs, then you'll be using not MOSFET because you've heard your MOSFET. You use IGBT. It stands for insulated gate bipolar transistor. I wouldn't go into details about the MOSFET mechanism and the IGBT mechanism. You just need to know that there are these two types of transistors, one for the low power and the other one is for high power. So there's another thing to note. As PWM increases, you get more of the back EMF because when you have on and off switching in your electrical circuit where your motor starts to rotate under PWM, then you get that back EMF that's coming from it as well. That's because for your motor, it's modeled with an inductor inside. So you have seen before in the 2 lectures ago, where I was modeling the motor with a resistor and an inductor. So that inductor would cause quite a fair bit of back EMF. So this PWM is used to generate an effective voltage output to your motor. And this effective voltage output to your motor maintains its polarity. That means I can lower down effective voltage by having PWM. But if you are interested to change the polarity, that means to have plus minus kind of sinusoidal wave as a PWM to your motor, that's also possible. Why is sine wave kind of voltage? Why are you interested in that for your motor? That's because there are so many motors out there. What you have seen before last time, when we have a motor, when I apply the electricity to your motor to cause it to rotate, I apply the current in one single direction because you have a commutator designed in that way. There's another type of motor that's called your AC motor with a slightly different construction. Let's see. Yeah, so you can see that the construction of this kind of motor with a commutator has 2 types of commutators over here. So your brushes will be over here, and your brush doesn't move, and your commutator will rotate as the wire rotates. Now this sort of configuration requires your electricity that's supplied to it to be alternating current. So then how can you supply an alternating current? Using your microprocessor and using PWM as well, positive modulation. The way to do it is to kind of like play around with your duty cycle with a varying duty cycle. So if you were to vary that duty cycle, the overall effect, right, the effective voltage that you get will become like an induction result. So if I were to do a sketch of this, let's do this few first part of it. Voltage. Time. Let's say the first one is over here. I'll give it a pulse of that certain duration. And let's say all these are my pulse separation, pulse separation, pulse separation. So the overall effect of this is that I'll get the effective voltage to be over here. And then I give the next pulse at say around here. So the effective voltage that I'll experience will be at this level. And then a third pulse that I vary its pulse duration, say up to here. So I get that kind of effect. So these are my average voltage output. So this is VCC. And what's going to happen is that you're going to get the overall effect that will join up the center part of this. So you can see that what I could do is to have this part over here that behaves overall as a sinusoidal effective voltage output. So this sinusoidal characteristic can be used to fit into my motor if I want it to give an AC if I want to give it an AC response. So those are the signals that you can do to change the behavior of your motor by using a PWM signal. Let's take a closer look at the how do we control the brush DC motor using a few strategies like H3. I need to define a few things. Now this figure is not in your notes. I just want to put it over here so that you understand why do we have two kinds of winding. Just very quickly. Now this part here is something that you've seen before. There's this brush over here, and then there's this commutator over here. And what's going on is that this armature over here would have this wire that's winding around it. So you've seen this before. And you've also seen before that after your armature winding, whatever that's surrounding over here is your magnet, your permanent magnet. But sometimes certain motor construction does not use magnet. In fact, it uses another coil over here to generate that magnetism. So now you can see that that permanent magnet can be self-generated electromagnetically in order to provide the presence of that magnetic fluid. So there's a co-sharing of these wires, the wire that's going around it. We call this coil over here as your armature winding, and we call that external coil over there as your field winding. Right? So later on we'll be making use of these two technologies, armature winding and your field winding. Your field winding is the one that's generating your magnetic flux instead of using a permanent magnet. So I could sketch, sometimes this kind of motor is called shunt wound DC motor. Shunt wound DC. Schematically, how it's designed is that way. You have an inductor, and then in parallel to it, you have your armature winding. So there'll be a current that's running through this. This is I current armature, and there's a current that's going through your field winding. That is I field. So this one is your field winding, and this one is your armature. So the speed of this rotation by your permanent magnet motor that you have seen before actually depends on the current that's going through your armature coil. So the higher amount of current that's going through your armature coil, the more higher speed your motor will take. And by changing that current, you can adjust the speed of your motor rotation. So usually we want to change the current that's going into your armature coil. Current that's going into your armature coil in order to change the speed of your motor rotation. We don't really change the field winding current that's going through it. We want to maintain a constant magnetic flux by your field winding. So in order to achieve that kind of result, changing the current that's going through your armature winding, what we need to do is to implement an electronic circuit of PWM signal going into your armature winding. So to give you an overview of how the MOSFET or the IGBT transistor is coming in. Normally we have the power supply connecting to your motor windings. So your motor windings would include your field winding and your armature winding. So that's your motor windings over here. And we need to have a diode over here. And this diode is required because of the inductive load over here. And what that means is that if you drive this plus, this minus, if you drive your motor, after you turn this down, if you drive your motor, you'll run that way. Right? And because there's this signal of PWM on and off, so that PWM signal is coming in. When it's on, that's fine, your motor is running. When it's off, that is when there's a breakage in here, because that's your off signal. So when there's a breakage in here, your motor will still continue to rotate. So as it continues to rotate, then there is this inductive loading that's coming in. And we need to apply this diode over here to help it to continue to rotate in help the current to continue to flow in that way around it, so that the motor will not get destroyed under your PWM signal. Because you can't have the current that's going in the opposite way if your motor is winding due to this momentum. So that's why we have this diode over here to accommodate that inductive load. So you can see that this kind of motor configuration with a diode. So normally we need to put a diode over here. This is necessary to prolong the life of the motor under a PWM signal. So this is kind of like schematically how each of the motor look like under PWM, right? This a typical motor setup. So then we're interested to find out how do we rotate the motor in the certain direction that we want. Because for your PWM, you cannot have a negative PWM. Your house is always positive house. Although recently there are also the negative PWM signals, but those are a little bit more complicated. What we can do in order to have your motor to rotate clockwise or anti-clockwise, conventionally we need to change the direction of your current so that it can rotate the other direction. But if we're using PWM, then how do we achieve that? You can do that by using this thing that's called H-bridge. Let's have a close look at how the H-bridge works. This is your motor over here. This is your plus voltage for your VCC, and that is your ground. So current will flow from plus VCC all the way to the ground. And in between here, you have either your MOSFET or your IGBT. And what you're going to do is that put it in this special H-bridge configuration, so that if you want the motor to go in the forward direction, this node over here will be high, and that node over there will be low. So let's have a look at high over here. If let's say you're using a MOSFET, you just need to supply higher than 2.4 volts, and it will give you a 1 signal. Low over here, anything that's less than 0.8 will give you a 0 signal. So if you have a high signal, what's going to happen is that this gate over here will turn on. So this MOSFET will be a through circuit. So this one is on, and that one is on. So this is on, that one is on. The other one, the other two, you have a low signal that's going in, so this is off. So essentially this is like a broken circuit. So you break the circuit over here, and then the other one over here, you're breaking that circuit. So now you have this and that as on. What's going to happen is that current is going to flow through this way, and you're going to drive your motor, and then you're going to come down to the ground that way. So your motor, say for example, will rotate in this direction, say clockwise direction. This is case one. So if you want to reverse the motor, what you could do then next is to reverse that high and low signal. So now let me use another color. So red color. So if this is low now and this is high, what's going to happen is that this will be a broken circuit, this will be a broken circuit, and this will be on, that will be turned on. So your VCC now will flow. You wouldn't flow this side because it's a broken circuit. Go down that way. Then go down there. This direction. So you can see now that your motor will rotate the opposite. So that's how we make use of your H-bridge to and PWM signal to rotate your motor in a clockwise or the anti-clockwise direction. So these are some techniques that you can use for your FYP or even for your Lego. Right? So your Lego robotics lab, if you want to make sure that you can adjust the speed of how fast your robot will move through your motor, which is your PC motor, then you can send a PWM signal. So if you want it to reverse back, then what you can do is to design this H bridge so that it could flow back, it could reverse back. Actually, your Lego toy already have this forward and reverse function, so they already take it like that. What is going on in the H bridge is that way. And the next slide sort of like outline what I've just said by labeling it like an S1, S2, turn on, and your S3 and S4 turn off. So you would run that voltage in one direction and the other one in the other direction. So you can see that each of these MOSFETs, we are modeled with a diode over there. Now the H-bridge is actually an open loop system, and in order for you to drive your motor, by using the H-bridge to control the clockwise and anti-clockwise direction, you may not achieve the exact position that you want, because there's no sense of feedback. So if you want some feedback to close the loop, to have a closed loop control system, what you could do is to apply a tachometer. Right? Because the tachometer is going to give you an error signal, so with that error signal, then you can decide have you really moved into a position that you want. But there is a problem. Let's have a look at this. You have your microprocessor, which is giving off a digital signal. So in order for your digital signal to be read by the motor, you need to convert that digital signal to an analog signal. So in order to do so, you need a DAC, the digital to analog converter. And normally your motor cannot be really driven by your microprocessor, because normally this signal over here maximum is about 5 volts or so coming up from your, say, Arduino. Your Arduino will send off the maximum 5 volts. 5 volts is actually not sufficient to drive all kinds of motors. some of the motors require 12 volts, or say even higher than that, 24 volts if you have a large motor. So if that's the case, usually you would have an amplifier to come in between to bump up your 5 volts to a higher voltage, say in this case 12 volts after amplification. So your motor would run, and there's no sense of where, in which position it ran to. So you need to check that output speed and put a tackle generator. Now the tackle generator will be a sensor. So this was covered in the topic of sensor. So the sensor, tackle generator, you have seen the mechanism before, and you would know that it's actually an analog sensor. So if you were to use the tackle generator as an analog sensor, then you must convert it back into a digital form so that the microprocessor could read, so as to tell it, is it reaching the kind of speed that you wanted. So this part here is the feedback.
人家的比较小，比较 Q， 我的太大。
So being a analog
公司要
device,
小
you
才
need
Q。
analog to digital converter to convert it back into a digital form so that the microprocessor can read. So you can see over this part here, it must be digital signal as going to your microprocessor.
中一个版。
Is there another way to do this instead of having an analog to digital converter? Actually, there is. You could use an encoder, because an encoder will be a digital device. But an encoder requires the code converter, because you have learned before for an encoder you get a series of 1 and 0 signals. So these 1s and 0 signals gotta be converted to tell us what is the position or the speed that is the motor has traveled. So you can use that encoder for this purpose. So the rest of it over here remains the same. The output speed there, if you want that output speed to be readable by your microprocessor, then you need either a analog tackle generator or a digital encoder. All encoders are digital. There's no analog encoder. How about the other part over here? So you have the encoder, digital converter, all seems good. I have this DAC converter over here to convert the signal from a microprocessor into an analog signal so as to drive my motor. So now you have learned that I can replace it using PWM. PWM is an on-off signal. It's a digital signal. Then how can I make my motor read that digital signal? What I could do is to have a PWM circuitry. So the pulses can run through a drive circuit. So in this case, a drive circuit could be a H-bridge so that you can control your motor in a clockwise or anti-clockwise direction. So your PWM circuitry can then send all the pulses to drive your motor. Your motor can be driven by PWM. PWM is sort of like an analog signal that is made into a digital form because it has this fully on, fully off kind of signal. So this fully on, fully off signal is the one that you use to drive your motor. At a certain switching frequency, you would have corresponding speed control to your motor. Could you check in your notes, is it F or E over here?
Nothing. E.
It's E. Please change that to F, because that F over there is filled. And then
更多东西耶，这全部都是。
So all these, please change that into an F. I think that's missing. Exactly. So what is this A and this F? So the A refers to your armature. Remember, I was showing you a motor with the armature winding. And your field winding is the one that's providing the magnetic flux. So this part over here. Without this part over here. So this one, the inner circuit, represents generation of constant external magnetic field. Across motor. So this is the part that's generating your permanent magnetic field, so that your armature would rotate. And this setup over here, actually don't have gears. So please note, in this case, there's no gear system. So it's a direct driving from a motor to a load. So that was the one that I was talking about. Recently, there are a lot of washing machines or things that requires a heavy duty motor to run. They sell it as a direct drive motor. A direct drive motor does not use gears. What it uses is this PWM signal, on and off signal, in order to change the speed of this motor. Direct drive motors are commercially sold as multi-roll. And there's a good reason why direct drive motors are multi-roll, because the signals that are going in is generated by electronic means, because you have the PWM circuit to generate that pulses. And these pulses allows us to adjust the speed of the motor. Had we not used PWM,
如果你有个 spare 的 condom， 你给它套上去。
the motor, we have to use the gear reduction ratio. And if you have gear systems in there, there's older washing machines, what's going to happen is that there's a higher chance of it breaking down, because more components, more mechanical components, more chances of failure. So that's why for a direct drive motor, you get it to be longer life lasting. Okay, there's going to be quite a fair bit of mathematics next. So what I'll do is to write it on one side. You'll see that a lot of it is very familiar, and we'll come back later after a short break